Have you ever wondered what secrets hide in the darkest corners of space, where light takes billions of years to reach us? Tonight, we journey beyond the edge of everything we know. Out there, in the silent void, the James Webb Space Telescope has been watching, waiting, collecting whispers from the ancient cosmos. It has seen things that challenge everything we thought was true about the universe. Galaxies that grew impossibly fast, black holes wandering alone through the dark, stars being torn apart and reborn in ways that defy our understanding. Let yourself drift through these cosmic wonders. Each discovery is a doorway into the unknown, a gentle reminder that reality is far stranger and more beautiful than we ever imagined. There are no loud narrations here, no jarring interruptions, just the slow unfolding of mysteries written in starlight and time. As you settle into this journey, the universe will reveal itself piece by piece. Ancient light from the first galaxies, silent travelers moving through endless night, forces we cannot see shaping everything around us. These are not stories of fear, but of wonder, of the infinite patience of the cosmos. If you find comfort in these quiet revelations, take a moment to like this video and subscribe to join us on more journeys through the universe. Your support helps us continue exploring the gentle mysteries of space. And now, let the stars guide you softly into dreams. Welcome to Sleepy Science Stories. In the quiet depths of space, 13 billion light years from Earth, something extraordinary awaits our discovery. The James Webb Space Telescope has gazed further into the cosmic darkness than any instrument before it, and what it reveals invites us to reconsider everything we thought we knew about the universe. Ancient galaxies existing against all expectations, black holes older than we imagined possible, and signals from distant worlds whispering across the emptiness. If you find peace in exploring the universe's deepest mysteries, consider sharing this journey, because what we're about to discover together will gently reshape how you perceive reality. Let us begin our voyage through the cosmos. The telescope itself represents a triumph of human ingenuity, floating in space at a location called Lagrange Point 2, nearly 1 million miles from Earth. At this gravitational balance point between our planet and the Sun, Webb maintains a stable position, its enormous golden mirror unfurled like a cosmic flower. The mirror spans 21 feet across, composed of 18 hexagonal segments coated in a microscopically thin layer of gold. This precious metal was chosen not for beauty, but for function, as gold reflects infrared light with exceptional efficiency. The telescope observes the universe in wavelengths invisible to human eyes, detecting the heat signatures of distant objects and the stretched light from galaxies so remote that their visible light has been redshifted into the infrared spectrum. A massive sun shield, as large as a tennis court, protects the sensitive instruments from the sun's warmth, keeping them cooled to temperatures just a few dozen degrees above absolute zero. In this extreme cold, Webb can detect the faintest whispers of heat from objects billions of light years away, revealing a universe that has remained hidden from all previous observers. Something curious is unfolding within the universe itself. For many decades, scientists believed they had measured how quickly our cosmos was expanding. The Hubble Space Telescope provided one set of numbers. Mathematical models suggested another. Everything appeared to align like pieces of an elegant cosmic puzzle. Then James Webb looked deeper than anyone had looked before, and the puzzle revealed unexpected complexity. The universe is expanding at two distinctly different rates, depending on where we observe it. Imagine a balloon being inflated, but one hemisphere stretches twice as quickly as the other. This scenario challenges our expectations. The laws of physics suggest that expansion should occur uniformly throughout all of space. Webb confirmed what astronomers had quietly wondered about. When they measured the expansion rate using distant stars called Cepheid variables, they found one value. When they calculated it using the cosmic microwave background radiation, they discovered a completely different value. These Cepheid variables are remarkable cosmic tools. They are stars that pulse with a regular rhythm, brightening and dimming in cycles that last days or weeks. The rate of their pulsation is directly related to their intrinsic brightness, making them excellent standard candles for measuring cosmic distances. By observing how bright a Cepheid appears from Earth, and comparing that to how bright it actually is, astronomers can calculate its distance with remarkable precision. Webb has observed these pulsating stars in galaxies across vast stretches of space, building a distance ladder that extends deep into the cosmos. Each rung of this ladder is carefully calibrated, connecting nearby Cepheids, whose distances we know precisely to more distant ones whose light has travelled for millions of years. The cosmic microwave background, by contrast, is the afterglow of the Big Bang itself, radiation that has travelled through space for nearly 14 billion years. By analysing the tiny temperature fluctuations in this ancient light, cosmologists can calculate how fast the universe was expanding in its earliest moments and predict how fast it should be expanding today. The difference is not subtle. We are observing a discrepancy so significant that it suggests our fundamental understanding of reality may need revision. Scientists call this the Hubble tension, but that name does not fully capture the profound nature of what we are encountering. This is not simply a measurement error or a calibration issue. After studying over 1,000 Cepheid stars across 5 separate galaxies stretching 130 million light-years into space, the contradiction persists. The implications invite contemplation. Either our models of how the universe operates are incomplete, or there is some unknown force shaping reality in unexpected ways. Dark energy, the mysterious component that drives cosmic expansion, might be behaving in ways we have not yet imagined. Some regions of space could be expanding more rapidly than others, creating cosmic patterns that challenge our current understanding of space-time. Adam Rees, the lead researcher exploring this puzzle, expressed it clearly. With measurement errors eliminated, what remains is the genuine and fascinating possibility that we have not yet fully understood the universe. The word fascinating feels appropriate when you consider what this means. If our basic understanding of cosmic expansion needs refinement, then our calculations about the universe's age, size, and ultimate journey are all open to reconsideration. Webb's remarkable precision has confirmed the reliability of the measurements. Both the telescope and Hubble are detecting the same intriguing contradiction. The universe is expanding, but it is doing so in a way that invites us to expand our understanding of physics. This discovery alone would be enough to inspire new cosmology textbooks. But Webb was just beginning its exploration. As the telescope continued its survey of deep space, it began finding objects that surprise us, behaviours that invite explanation, and phenomena that suggest our reality is far more intricate and wondrous than we had imagined. The expansion puzzle was only the first of a series of discoveries that would encourage scientists to question and refine everything they thought they knew about the cosmos. But what Webb found next adds another layer of wonder to our cosmic story. 6 remarkable structures are floating in the ancient cosmos, and they are reshaping our understanding of galactic evolution. When James Webb pointed its infrared eyes toward a seemingly quiet patch of sky near the Big Dipper, astronomers expected to find small young galaxies moving through their first billion years of existence. Instead, they discovered 6 massive, mature star systems that appear to have grown unusually large. These galactic giants contain nearly as many stars as our own Milky Way, but they formed when the universe was only 3% of its current age. Picture trying to grow a full-sized oak tree in just 3 months. That is essentially what these galaxies accomplished on a cosmic timescale. Star formation requires time. gravity needs millions of years to gather enough gas and dust to ignite nuclear fusion. Yet these 6 systems somehow accelerated their development, becoming galactic titans while the universe was still in its cosmic infancy. The discovery unfolded almost unexpectedly. Astrophysicist Erica Nelson was examining small sections of Webb's deep field images when she spotted several fuzzy red dots that appeared remarkably bright. Red light in astronomy usually indicates ancient light stretched by the universe's expansion during its long journey to Earth. But these objects were both ancient and intensely luminous, a combination that invites deeper investigation. Each of these massive galaxies contains between 10 billion and 100 billion stars. To reach such enormous sizes so quickly, they would have needed to form hundreds of new stars every single year for hundreds of millions of years. Our Milky Way, by comparison, creates only about 2 new stars annually. These ancient systems were stellar factories operating at production rates that surprise our current models of physics. The team has informally nicknamed these objects universe breakers because they challenge our understanding of how cosmic structures form. According to every simulation and model scientists have created, matter in the early universe should have gathered together slowly and methodically. Small structures would gradually merge to form larger ones over billions of years. These 6 galaxies invite us to reconsider that entire timeline. They suggest that the early universe was capable of organization and complexity that cosmologists had not imagined possible. Either there is a mechanism for rapid galaxy formation we have not yet discovered, or our fundamental assumptions about cosmic evolution need refinement. The discovery raises intriguing questions about dark matter's role in early cosmic development. If galaxies could grow this massive this quickly, it means dark matter was gathering together and attracting regular matter at rates exceeding current predictions. The invisible framework that shapes our universe might be far more dynamic and complex than we realized. Joel Leisure, one of the astronomers studying these objects, captured the significance perfectly. We looked into the very early universe for the first time and discovered something so unexpected that it creates genuine opportunities for advancing science. But confirming the nature of these objects will require additional observations with Webb's spectrograph. And what those follow-up studies revealed would prove even more intriguing than anyone anticipated. As we contemplate these ancient galaxies, it helps to consider the nature of deep space observation itself. When Webb gazes at objects 13 billion light years away, it is not merely seeing distant places, but distant times. The light reaching the telescope today began its journey when the universe was young, travelling across expanding space for most of cosmic history. We are witnessing not the galaxies as they are now, but as they were in that ancient era. Those galaxies have continued evolving, growing, merging with neighbours, perhaps transforming into completely different structures. But we will never see those changes. The light, showing us their current state, will not reach Earth for billions of years, and by then, our sun will have long since exhausted its fuel. In a profound sense, the past is the only distant place we can ever observe. The farther we look into space, the deeper we peer into history, watching the universe's story unfold across cosmic time. This phenomenon of look-back time creates a unique challenge and opportunity for astronomy. Webb's observations are not just spatial, but temporal, showing us the universe at different evolutionary stages depending on the distance of the objects it observes. A galaxy 1 billion light years away is seen as it was 1 billion years ago. A galaxy 10 billion light years distant appears as it looked when the universe was less than a quarter of its current age. By surveying galaxies at many different distances, Webb essentially creates a timeline of cosmic evolution, observing how galaxies, stars, and black holes have changed over the vast sweep of cosmic history. The telescope's ability to observe the universe's past also means that some of the objects it images may no longer exist in their observed forms. A massive star that Webb observes exploding as a supernova in a distant galaxy actually exploded millions or billions of years ago. That star's light is only now reaching us, carrying information about an event long concluded in the star's own time frame. In this sense, Webb is not just a telescope, but a cosmic time machine, allowing us to witness the universe's history directly. A monster with the mass of 50 million suns is traveling through space in remarkable isolation, and it is reshaping our understanding of cosmic history. Deep in the early universe, James Webb discovered something that challenges every theory of black hole formation. Quasar Joan 148 contains a supermassive black hole with virtually no galaxy surrounding it. It is essentially unaccompanied, drifting through space without the typical host of billions of stars that normally accompany such massive objects. Most supermassive black holes reside at the centers of galaxies like cosmic anchors, surrounded by spinning disks of stars, gas, and dust. They form a relationship with their galactic hosts, growing together over billions of years through a delicate interplay of gravity and star formation. This object breaks those familiar patterns. This cosmic wanderer contains enough mass to equal 50 million of our suns, compressed into a region smaller than our solar system. To put that in perspective, if you could somehow stand at a safe distance and observe this black hole, its gravitational pull would be warping space-time so severely the light itself bends in visible arcs around its edge. The object exists in a region of space where the universe was only about 700 million years old, barely 5% of its current age. At that early cosmic moment, galaxies were supposed to be small, primitive structures, just beginning to organize themselves from clouds of primordial gas. Finding a fully mature supermassive black hole at this time is like discovering a sophisticated smartphone in an archaeological dig from ancient Rome. The technology, or in this case the cosmic structure, simply should not exist at that point in history. Traditional black hole formation theory suggests these massive objects grow through two main pathways. Either they form from the collapse of the first generation of stars, growing gradually by consuming nearby matter over billions of years, or they emerge from direct collapse of massive gas clouds in the early universe. Both processes take time, a lot of time. To reach 50 million solar masses through stellar collapse would require consuming the equivalent of an entire small galaxy worth of matter, star after star, gas cloud after gas cloud, over hundreds of millions of years. But this black hole appears to have achieved that mass in a fraction of that expected timeline. What makes this discovery even more puzzling is the absence of a surrounding galaxy. Supermassive black holes and their host galaxies are supposed to grow together through cosmic evolution. The black hole's gravity pulls in gas that forms stars, and those stars eventually die and feed more matter back into the black hole. It is a cosmic cycle that creates the beautiful spiral and elliptical galaxies we see throughout the universe. But Quasar Joan 148 is missing that entire structure. The black hole appears to have formed and grown without building a traditional galactic home. Either it consumed its entire galaxy already, which would require violating our understanding of how quickly black holes can consume matter, or it formed through some completely unknown mechanism that bypasses galactic formation entirely. Scientists studying this object have proposed several explanations, each one challenging fundamental assumptions about cosmic evolution. Perhaps black holes in the early universe could grow much faster than current physics predicts. Maybe the density of matter in certain regions of the young cosmos allowed for rapid feeding that is impossible in today's more dispersed universe. Or possibly, there is an entirely unknown pathway for black hole formation that operates only under the extreme conditions present shortly after the Big Bang. The discovery also raises quiet questions about how common these wandering supermassive black holes might be. If one exists in the small patch of sky Webb has surveyed, there could be thousands or millions of similar objects drifting through intergalactic space, invisible except when they actively consume matter and glow as quasars. The cosmic census we have been building for decades might be missing an entire population of massive objects moving through the darkness. Christina Eilers, the astrophysicist leading the research, expressed the significance simply. Finding this object was a tremendous surprise. It is one of the most extreme objects we have found, and its mere existence challenges our understanding of black hole and galaxy formation in the early universe. But as remarkable as this lone wanderer is, it represents just one thread in the tapestry of mysteries Webb has revealed. The telescope's continued observations would soon uncover phenomena even stranger, forcing astronomers to question whether our cosmic neighborhood is as stable and predictable as we once believed. The behavior of matter near black holes is itself a study in extremes. As gas spirals inward toward the event horizon, friction heats it to millions of degrees, causing it to glow brilliantly across multiple wavelengths. The innermost regions of these accretion disks orbit at significant fractions of light speed, completing a full circle in mere hours despite encompassing distances greater than our solar system. Time itself behaves strangely here. An observer watching from a safe distance would see time appear to slow for objects approaching the event horizon, with falling matter seeming to freeze at the boundary as gravitational time dilation becomes extreme. Yet from the perspective of that falling matter, time would pass normally and the journey inward would proceed without hesitation. This profound disconnect, where different observers witness fundamentally different realities, illustrates how thoroughly gravity can reshape the nature of space-time and our experience of it. Among the most remarkable aspects of Webb's black hole observations is its ability to detect variations in the accretion disk on surprisingly short timescales. The disk of matter spiraling around a black hole is not a stable, unchanging structure, but a turbulent, dynamic environment where conditions change rapidly. Webb has observed brightness variations that occur over days or even hours, indicating that matter is falling into the black hole in discrete chunks rather than a smooth, continuous flow. These variations provide clues about the structure of the accretion disk and the nature of the material being consumed. The telescope has also revealed evidence of magnetic fields in the gas surrounding black holes. These fields, though invisible, leave signatures in the polarization of light emitted by the hot plasma. By analyzing how light is polarized, astronomers can map the geometry and strength of these magnetic fields. The fields play a crucial role in channeling matter toward the black hole and launching the powerful jets that stream away from some black holes at speeds approaching the speed of light. Understanding these magnetic processes helps explain how black holes can have such profound effects on their environments despite their relatively small physical size. Galaxies across vast regions of space are spinning in coordinated patterns, and this cosmic choreography invites us to reconsider the fundamental structure of the universe. When James Webb conducted its deep survey of distant galaxies, astronomers discovered something that should not be possible according to our current cosmological models. Galaxies separated by millions of light years, far beyond any range where gravity could coordinate their motions, are rotating in aligned directions. Think of it like finding hundreds of spinning tops scattered across an entire continent, all rotating clockwise or all rotating counterclockwise, despite having no physical connection to one another. In a universe that formed from the random quantum fluctuations of the Big Bang, galactic rotation should be essentially random. Some galaxies should spin one way, others the opposite way, with no pattern or preference across large cosmic distances. But Webb's observations reveal a different reality. When scientists analyzed the rotation of galaxies across multiple clusters and superclusters, they found alignments that persist across scales of hundreds of millions of light years. The galaxies are not just randomly spinning, they are participating in large-scale patterns that suggest some kind of cosmic organization we do not yet understand. The discovery builds on earlier observations from ground-based telescopes that hinted at these patterns, but Webb's unprecedented sensitivity and range have confirmed that the alignments are real and extend deeper into cosmic history than anyone expected. In some regions of space, up to 56% of galaxies share the same rotational orientation. This is far higher than the 33% you would expect from pure chance. The excess alignment indicates that some physical process is coordinating galactic spin across cosmic distances. Several explanations have been proposed, none of them comfortable within our current cosmological framework. Perhaps the early universe had some kind of preferred rotation axis imprinted during the Big Bang, a cosmic spin that manifested as galaxies formed and began their own rotations. Or maybe the distribution of dark matter, the invisible substance that makes up most of the universe's mass, is not as uniform as we thought. If dark matter forms large-scale filaments and sheets with preferred orientations, those structures could influence how galaxies spin as they form within the dark matter framework. The implications extend beyond just galactic rotation. If the universe has large-scale structure and organization that we have not accounted for in our models, it could affect everything from cosmic expansion calculations to our understanding of how structure formed in the early cosmos. The aligned galactic spins suggest that the universe might have memory, a way of preserving information about its earliest moments that persists billions of years later in the rotation of galaxies. This challenges the cosmological principle, the foundational assumption that the universe is essentially the same in all directions and locations when viewed at large enough scales. Scientists have proposed that cosmic magnetic fields stretching across intergalactic space might play a role in coordinating galactic rotation. These magnetic structures, far weaker than even Earth's magnetic field, but extending over incomprehensibly vast distances, could have influenced the angular momentum of gas clouds as they collapse to form galaxies. Another possibility involves the cosmic web itself, the large-scale structure of filaments and voids that organizes matter throughout the universe. If galaxies form within these filaments and preferentially align their rotation with the filament's orientation, it could create the patterns Webb is observing. But this explanation requires the cosmic web to have more regularity and organization than current simulations predict. The discovery of coordinated galaxy rotation joins a growing list of large-scale cosmic anomalies that challenge the standard model of cosmology. When combined with the expansion rate discrepancies and the unexpectedly massive early galaxies, a picture emerges of a universe that is more structured, more organized, and more mysterious than our theories predict. Shamir Lior, whose research has focused on galactic rotation patterns, summarized the situation thoughtfully. These observations suggest that the universe may have large-scale structure or physical processes that are not accounted for in current cosmological models. As Webb continues its survey of the cosmos, each new observation adds detail to this emerging picture of cosmic organization. The universe is not just a random collection of galaxies scattered through space. It is a cosmos with patterns, alignments, and structures that span its entire observable volume, inviting us to discover the principles that govern its grandest architecture. But the mysteries of galactic rotation would soon be joined by discoveries even more profound. Webb's exploration of the early universe was about to reveal objects that challenge not just our models of galaxy formation, but our entire understanding of cosmic chronology. Black holes that formed before stars even existed are floating in the primordial universe, and they are rewriting the timeline of cosmic evolution. According to everything we thought we knew about the early universe, the first stars formed about 100 to 200 million years after the Big Bang. These stellar pioneers, made entirely of hydrogen and helium, lived brief violent lives before exploding and seeding space with the heavier elements that would make later generations of stars possible. Black holes were supposed to come later, forming either from the collapse of massive stars or from the direct collapse of extremely dense gas clouds. The sequence seemed clear: first light, then stars, then black holes, then galaxies organizing around those black holes. James Webb has found black holes that predate this entire sequence. In multiple observations of the extremely early universe, Webb has detected supermassive black holes that appear to have formed when the cosmos was less than 500 million years old. Some of these objects seem to exist even earlier, in an era when the universe was barely 200 million years old. At those cosmic moments, there had not been enough time for traditional black hole formation pathways to produce such massive objects. These primordial black holes challenge the entire narrative of cosmic structure formation. If black holes existed before stars, where did they come from? How did they form? And what role did they play in shaping the early universe? One possibility is that these black holes formed directly from the collapse of massive regions of primordial gas in the very early universe. If conditions were right, gravity could have caused entire clouds of hydrogen and helium to collapse straight into black holes without ever forming stars. This would require specific and perhaps rare configurations of density and temperature in the young cosmos, but it would explain how massive black holes could appear so quickly. Another, more intriguing possibility is that these black holes are remnants from the Big Bang itself, primordial black holes that formed directly from density fluctuations in the first moments of cosmic time. If this is true, these objects are not just ancient, they are primordial, older than atoms, older than the first particles, as old as time itself. The existence of black holes before stars also raises questions about their influence on early cosmic evolution. Black holes are not passive objects. They pull in surrounding matter, heat it to tremendous temperatures, and blast radiation across space. If supermassive black holes existed in the very early universe, their energy output could have significantly affected how the first stars and galaxies formed. We might need to completely revise our models of cosmic dawn, the era when the universe transitioned from darkness to light, to account for the presence of these early black holes. Their gravitational influence could have created regions where star formation happened more quickly, or conversely, regions where their radiation suppressed star formation entirely. The distribution of galaxies we see today might be shaped in part by the locations of these primordial black holes. Webb's discovery also impacts our understanding of supermassive black holes in general. If such massive objects could form very early in cosmic history, it suggests that the pathway to creating billion solar mass black holes might be more efficient than we realized. This could explain why virtually every large galaxy we observe contains a supermassive black hole at its center. Maybe these black holes formed first, and galaxies assembled around them, rather than galaxies forming first and black holes growing within them. The timeline of events in the early universe is being rewritten with each new observation. What once seemed like a clear sequence of development now appears far more complex and interconnected. Stars, black holes, and galaxies may have emerged in a chaotic and overlapping process, each influencing the formation of the others in ways we are only beginning to understand. Priyamvada Natarajan, an astrophysicist studying these early black holes, described the significance. These discoveries are transforming our understanding of when and how the first black holes formed. We are watching the universe's earliest structures emerge in ways that surprise our models, but the story of early cosmic evolution has more unexpected chapters. As Webb continued probing the ancient universe, it would discover evidence of violence and upheaval that suggests the first billion years of cosmic history were far more turbulent than anyone imagined. Massive galaxies in the early universe are violently colliding and merging at rates that surprise our models of cosmic evolution. When James Webb turned its attention to galaxy clusters in the young universe, astronomers expected to see orderly, gentle growth. Small proto-galaxies gradually pulling together under gravity's patient influence. Instead, Webb revealed a cosmos in chaos, a universe where massive galaxies were smashing together in spectacular collisions that reshaped their structures and triggered intense bursts of star formation. These collisions are happening far more frequently in the early universe than current models predict. In some regions of space that Webb surveyed, more than 30% of massive galaxies show clear signs of recent or ongoing mergers. This is significantly higher than the merger rate in the modern universe, where galactic collisions are relatively rare events. The violence of these early mergers is reshaping our understanding of how galaxies grow. When two large galaxies collide, their stars rarely actually hit each other, separated by such vast distances that direct collisions are nearly impossible. But the clouds of gas between the stars slam together with tremendous force, compressing and heating until vast regions ignite in furious waves of star formation. Webb can see these starburst regions glowing brilliantly in infrared light, creating hundreds or even thousands of new stars every year, compared to the sedate 1 or 2 stars per year that form in quiet galaxies like our current Milky Way. The mergers also feed the central black holes of both galaxies, sending torrents of gas spiraling inward to be consumed. As the black holes feast, they blast out jets and winds of superheated matter that can be seen across millions of light years. These energetic outflows, in turn, affect the surrounding intergalactic medium, enriching it with heavy elements and potentially triggering or suppressing star formation in nearby regions. What makes these discoveries particularly significant is their timing. These violent mergers are happening when the universe is less than 2 billion years old, a period when galaxies were supposed to be building themselves gradually through the accretion of smaller structures. The high merger rate suggests that the early universe was far more dynamically active than cosmological simulations have shown. The distribution of dark matter in the young cosmos may have been clumpier and more turbulent than we modelled, leading to more frequent close encounters between forming galaxies. The observations also reveal unexpected structures within these merging systems. Some show multiple nuclei, the combined cores of several galaxies all spiraling toward an eventual union. Others display vast tidal tails, streams of stars and gas pulled out by gravitational forces during the collision. These features provide clues about the dynamics of the merger and the properties of the galaxies involved. Understanding these early mergers is crucial for understanding how modern galaxies formed. Our Milky Way almost certainly experienced numerous mergers throughout its history, gradually building up its current mass by consuming smaller galaxies. The Andromeda Galaxy, our nearest large neighbour, is currently on a collision course with the Milky Way, though they will not merge for another 4 billion years. By studying the violent mergers in the early universe, astronomers can better understand the processes that shaped our own galactic home. The frequency of these collisions also affects the rate at which the universe builds up heavy elements. Each generation of stars produces elements heavier than hydrogen and helium, spreading them through space when the stars die. Mergers accelerate this process by triggering intense star formation and distributing those elements more widely through the energetic outflows from central black holes. Webb's observations suggest that the chemical enrichment of the universe happened more quickly than previously thought. Within the first 2 billion years, some regions of space had already reached chemical compositions similar to what we see in the modern universe. This rapid enrichment could have implications for when and where planets capable of supporting life could form, since such worlds require elements heavier than hydrogen and helium. The discovery of frequent early mergers also connects to the mystery of the impossibly massive early galaxies that Webb discovered. Perhaps those galaxies grew so large so quickly because they were built through a rapid series of mergers in the dense environment of the young universe, rather than through the slow, steady accretion that builds galaxies in later cosmic eras. As Webb continues to observe these cosmic collisions, astronomers are building a new picture of galactic evolution, one where violence and upheaval play a larger role than previously imagined. The early universe was not a place of gentle formation and gradual growth. It was a dynamic, energetic era where galaxies crushed together, black holes gorged themselves, and star formation erupted in brilliant waves across the cosmos. Within these merger events, individual stellar systems experienced their own transformations. Star clusters born in the collision's starburst regions can contain hundreds of thousands of young, brilliant stars packed into volumes just a few dozen light-years across. The combined luminosity of these clusters rivals entire small galaxies. Some of these clusters will survive for billions of years, eventually becoming the globular clusters that orbit mature galaxies like ancient jewels. Others will be disrupted by gravitational interactions, their stars scattered throughout their host galaxy to join the general stellar population. The fate of planetary systems during these mergers is a topic of quiet contemplation. Most planets orbit their stars at distances large enough that even close stellar encounters would not disturb them. But planets in the outer regions of their systems, or those orbiting stars that pass unusually close to other stars during the merger, might be ejected, becoming the road planets that wander through interstellar space. The galaxy merger process, while spectacular on cosmic scales, unfolds over tens of millions of years, giving most planetary systems time to adapt to their changing gravitational environment. But merger violence was not the only surprise Webb had in store. The telescope's exploration of the early universe would soon reveal another class of objects that challenge our cosmic timeline, structures so unexpected they have forced astronomers to question fundamental assumptions about what was possible in the ancient cosmos. Mature globular clusters are floating around distant galaxies that are supposed to be too young to host such ancient structures, and they are challenging our timeline of cosmic evolution. Globular clusters are among the most beautiful objects in the night sky, dense spherical collections of hundreds of thousands of stars bound together by gravity. They orbit the outskirts of galaxies like cosmic jewels, their ancient stars glowing with a golden light that speaks to their tremendous age. In our Milky Way, globular clusters are relics from the galaxy's youth, formed when our cosmic home was still assembling itself billions of years ago. James Webb has found similar globular clusters surrounding galaxies in the very early universe, when those galaxies themselves should barely have begun to form. These clusters contain stars that appear to be several 100 million years old, existing around galaxies that are only slightly older. It is like discovering medieval castles on an island that supposedly only emerged from the ocean a decade ago. The timeline does not work. For globular clusters to form and age several 100 million years requires that much time to have passed since their formation. But if these clusters exist around galaxies in the early universe, it means they had to have formed even earlier, perhaps within the first few 100 million years after the Big Bang, a period when conditions were supposed to be too chaotic and turbulent for such stable structures to assemble. The discovery challenges our understanding of when the first stars formed and how quickly they could organize into stable clusters. Traditional models suggest that the very first stars were lone massive objects, population 3 stars made entirely of primordial hydrogen and helium. These stars were supposed to live and die in isolation before later generations could form clusters. But if globular clusters existed in the very early universe, it suggests that stars could form in groups from the beginning, organizing immediately into the dense stellar collections we see as globular clusters today. This would require a different model of star formation in the early cosmos, one where gravity could efficiently gather gas into compact regions where thousands of stars could ignite nearly simultaneously. the presence of mature globular clusters in young galaxies also affects our understanding of galactic assembly. In current models, globular clusters form during major episodes of star formation, often triggered by galaxy mergers. The clusters then survive for billions of years, orbiting their host galaxy as long-lived relics of that formative period. If Webb is finding mature clusters around very young galaxies, it suggests that either these galaxies experienced their formation episodes extremely early, or that globular clusters can form through mechanisms we have not yet identified. The clusters Webb has observed also show unexpected chemical compositions. Some contain higher levels of heavy elements than should exist in the very early universe, suggesting they have either experienced unusual enrichment from nearby supernovae or that the universe's chemical evolution proceeded more rapidly in some regions than our models predict. These observations connect to other mysteries Webb has revealed about the early cosmos. The impossibly massive galaxies, the premature black holes, and now the mature globular clusters all point toward a common theme. The early universe was capable of organizing matter and building complex structures far more efficiently than we believed possible. Something about the conditions in the young cosmos, whether it was the density of matter, the behavior of dark matter, or some entirely unknown factor, allowed rapid development that our current physics struggles to explain. Studying these early globular clusters also provides clues about the nature of the first stars. By analyzing the light from cluster stars, astronomers can determine their age, composition, and formation history. This information helps constrain models of what the very first generation of stars was like and how they influenced their surroundings. Some researchers have proposed that globular clusters might actually be the surviving remnants of the first small galaxies, dense protogalactic structures that were later captured by larger galaxies and stripped of their outer stars, leaving only the dense central cores we see as clusters today. If true, this would mean globular clusters are not just collections of old stars, but actually the fossils of cosmic dawn, the remnants of the very first luminous structures in the universe. The discovery of mature globular clusters in the early universe adds another layer to the emerging picture of rapid cosmic evolution. Each new Webb observation seems to push back the timeline for when complex structures could form, compressing the development of the cosmos into a shorter and more intense period than we imagined. But structure formation in the early universe represents only part of the story Webb is revealing. The telescope's observations have also uncovered evidence of phenomena that challenge not just our models of cosmic evolution, but our understanding of physics itself. Distant galaxies are connected by vast bridges of matter spanning millions of light years, and these cosmic threads are revealing patterns in the universe's large-scale structure that invite deeper understanding. When James Webb conducted its surveys of galaxy clusters, it did not just observe the galaxies themselves. The telescope also detected the faint filaments of gas and dark matter that connect galaxies across intergalactic space, creating a vast cosmic web that spans the entire observable universe. These filaments had been predicted by cosmological simulations, but Webb's observations provide the first detailed direct views of their structure and composition. The cosmic web forms because matter in the universe is not distributed evenly. Instead, it follows the distribution of dark matter, which clumps together under its own gravity into sheets, filaments, and nodes. Regular matter, the atoms and molecules that make up stars and gas, flows along these dark matter structures, like rivers following the contours of a landscape. Galaxies form where these filaments intersect, at cosmic crossroads where matter accumulates in sufficient density to trigger star formation. Webb's observations reveal that these filaments are more structured and complex than simulations predicted. Some show clear streams of gas flowing from one galaxy to another, feeding star formation in the receiving galaxy. Others display shock waves and turbulence, evidence of matter flowing at high speeds through the intergalactic medium. The telescope can detect these features because the gas in the filaments is not completely dark. It glows faintly in specific wavelengths of light, emitting photons when electrons in hydrogen atoms transition between energy levels. By tuning to these specific wavelengths, Webb can map the distribution of gas along cosmic filaments, creating detailed images of the universe's scaffolding. What makes these observations particularly valuable is that they reveal how galaxies interact with their environment. Galaxies are not isolated islands floating in empty space. They are part of a vast interconnected system, constantly exchanging matter and energy with their surroundings through these cosmic filaments. Some galaxies are actively pulling in fresh gas from the filaments, fueling ongoing star formation. Others are pumping matter back out into intergalactic space through supernova-driven winds and black hole jets. This cycle of inflow and outflow regulates how galaxies grow and evolve over cosmic time. The structure of the cosmic web also affects where different types of galaxies form. Galaxies at the intersections of multiple filaments tend to be massive elliptical galaxies, having consumed large amounts of matter from the surrounding web. Galaxies along individual filaments are often spiral galaxies like the Milky Way, drawing in matter more gradually and maintaining active star formation. Isolated galaxies in the voids between filaments, rare but fascinating objects, evolved in relative solitude with limited access to external matter sources. Webb's observations of the cosmic web extend back into the early universe, showing how this structure evolved over time. In the young cosmos, the filaments were denser and more prominent, feeding rapid galaxy growth and frequent mergers. As the universe expanded and matter dispersed, the filaments became more tenuous, and galaxy evolution slowed to the more sedate pace we observe in the modern cosmos. The discovery of detailed cosmic web structure also helps astronomers test cosmological models. Computer simulations of cosmic evolution predict specific patterns of filament distribution based on assumptions about dark matter properties, initial conditions in the early universe, and the values of fundamental constants. By comparing Webb's observations with simulation predictions, researchers can determine whether our models accurately capture how cosmic structure forms. Some of the observed filament properties match simulations well, confirming aspects of the current cosmological model. But other features, such as the apparent strength of some filaments and the flow speeds of gas through them, differ from predictions, suggesting refinements to the models may be needed. The cosmic web observations also connect to mysteries about dark matter itself. The distribution of filaments traces dark matter structure, and any unexpected patterns could provide clues about dark matter's nature. If dark matter interacts with itself in ways beyond simple gravity, those interactions should leave signatures in how filaments form and evolve. Webb's observations provide data that can help constrain these possibilities, potentially narrowing the vast range of theoretical dark matter candidates. As we gaze at images of the cosmic web revealed by Webb, we are seeing the universe's fundamental architecture, the underlying structure that determines where galaxies form, how they evolve, and ultimately where conditions suitable for planets and perhaps life can arise. We are not inhabitants of random space, but residents of a specific location within this vast organized network, connected through invisible threads to galaxies millions of light years away. The cosmic web also tells us something profound about the nature of empty space. The vast voids between filaments are not truly empty, but contain extremely diffuse gas at temperatures of millions of degrees, heated by shock waves from structure formation and by energy from galaxies and quasars. These voids comprise most of the universe's volume, yet contain relatively little mass, creating a cosmic structure more akin to foam or sponge than to a uniform distribution of matter. The contrast between dense filaments and empty voids is one of the universe's most striking large-scale features, a pattern that emerged from tiny quantum fluctuations in the first moments after the Big Bang and grew over billions of years into the magnificent structure we observe today. But while the cosmic web reveals organizational principles operating on the largest scales, Webb's exploration of the smallest scales would uncover phenomena equally profound. The telescope's study of planetary systems and stellar evolution was about to reveal surprises that challenge our understanding of how worlds form and what conditions might support life. Rogue planets are drifting through interstellar space in far greater numbers than expected, and some of them are broadcasting mysterious signals into the void. When James Webb surveyed nearby star-forming regions, astronomers hoped to catalogue young planets still forming around their parent stars. They found those expected planets, but they also discovered something unexpected: numerous massive Jupiter-like worlds floating freely through space with no star to orbit. These rogue planets, also called free-floating planetary mass objects, had been detected before in small numbers. But Webb's sensitivity has revealed that they might be incredibly common, potentially numbering in the billions throughout our galaxy. How these worlds ended up adrift is a matter of ongoing investigation. Some likely formed around stars and were later ejected through gravitational interactions with other planets or passing stars. Others might have formed directly from the collapse of small gas clouds, more like tiny failed stars than true planets. Regardless of their origin, these wandering worlds present a curious phenomenon. They are unexpectedly active. Several of the rogue planets Webb observed are emitting radio signals, faint but detectable broadcasts at specific frequencies. These signals are not artificial. They are natural emissions generated by interactions between the planet's magnetic fields and charged particles in their atmospheres, similar to the radio auroras that Jupiter produces in our own solar system. But the strength and characteristics of these emissions are puzzling. For a rogue planet with no nearby star to provide energy, maintaining a strong magnetic field and active atmosphere requires internal heat. Jupiter, for example, radiates more heat than it receives from the Sun, warming itself through slow gravitational contraction and possibly through residual heat from its formation. Rogue planets should behave similarly, but some of Webb's observations suggest higher activity levels than simple cooling can explain. One possibility is that these worlds are heated by radioactive decay in their cores, with enough uranium, thorium, and potassium to maintain geological activity for billions of years. Another intriguing possibility is that some rogue planets host moons, and the gravitational interaction between planet and moon generates tidal heating, keeping both bodies warmer than they would be in isolation. This scenario is particularly interesting because it suggests rogue planets could potentially support conditions suitable for life, not on their surfaces, but in subsurface oceans warmed by tidal forces. The radio signals from rogue planets also provide a way to detect and study these otherwise invisible objects. Unlike planets around stars, which we can find by watching for the dimming of starlight or the wobble of the star's position, rogue planets produce almost no visible light. They are dark worlds drifting through dark space. But if they emit radio waves, we can detect them with radio telescopes, potentially allowing a complete census of the rogue planet population in our galactic neighborhood. Some of the signals Webb helped characterize show patterns that invite investigation. Periodic variations in signal strength, suggestive of rotating magnetic fields or structured atmospheric phenomena. Researchers have even speculated, though cautiously, whether extremely advanced civilizations might somehow make use of rogue planets as vessels for interstellar travel, harnessing their resources while drifting through the galaxy. While this remains entirely speculative, the presence of active, potentially warm rogue planets does expand the range of environments we consider when thinking about where life might exist. The discovery of numerous rogue planets also affects our understanding of planetary system formation. If planets are commonly ejected during the formation process, it means that many, perhaps most, planetary systems go through a violent early phase where gravitational interactions shuffle the orbits of young worlds. Our own solar system likely experienced similar chaos, with planets migrating inward and outward before settling into their current stable orbits. Some models suggest that our solar system might have originally contained additional giant planets that were ejected billions of years ago, now wandering as rogue worlds somewhere in the galaxy. The study of rogue planets connects to broader questions about the universe's habitability. If billions of Earth-sized rogue planets exist with subsurface oceans kept liquid by internal heat, they could represent an entirely separate category of potentially habitable worlds, unconnected to any star, following their own independent paths through the cosmos. Life on such worlds would face unique challenges, deprived of starlight and unable to harness solar energy through photosynthesis. But Earth's deep ocean vents demonstrate that ecosystems can thrive based on chemical energy alone, independent of sunlight. A rogue planet with a warm core and active geology could potentially support similar chemosynthetic life in underground or under ice oceans. As Webb continues to observe and characterize these wandering worlds, we are developing a richer picture of planetary diversity in the galaxy. Planets are not just companions to stars, but independent cosmic entities that can exist and remain active even in the darkness between stars. The implications for astrobiology extend beyond just rogue planets. Webb's discoveries about the prevalence of organic molecules in space, from complex hydrocarbons in nebulae to amino acid precursors in cometary ices, suggest that the chemical building blocks of life are common throughout the universe. These molecules form naturally through chemical processes in space, driven by starlight, cosmic rays, and the energy released by stellar explosions. If the ingredients for life are so widespread, it raises the possibility that life itself might be more common than we previously imagined, arising wherever conditions allow chemistry to become biology. The telescope has also observed water vapor in the atmospheres of planets throughout our galaxy and detected water ice in regions where new planets are forming. Water is essential for life as we know it, serving as a solvent that enables complex chemistry and as a medium for biological processes. Finding water so commonly distributed across the universe suggests that potentially habitable environments might be far more numerous than early estimates suggested. Yet the transition from chemistry to biology remains mysterious. We do not fully understand how non-living matter organizes itself into living systems, and until we observe life beyond Earth or successfully create it in laboratories, the question of life's cosmic frequency will remain one of the deepest unknowns in science. But rogue planets represent only one thread in the tapestry of Webb's discoveries about planetary systems. The telescope's observations of planets around other stars have revealed atmospheric compositions and climatic conditions that challenge our assumptions about habitability and planet formation. Distant exoplanets are displaying atmospheric chemistry that defies our models of planetary formation and evolution. When James Webb turns its powerful instruments toward planets orbiting other stars, it can analyze the composition of their atmospheres by observing how starlight filters through the thin layer of gas surrounding each world. Different molecules absorb light at specific wavelengths, creating a unique spectral fingerprint that reveals what gases are present. Some of the atmospheres Webb has analysed contain molecules that should not coexist. Combinations of gases that react with each other chemically and should not persist for long periods in planetary atmospheres. Yet there they are, somehow maintained in chemical disequilibrium, suggesting active processes replenishing them faster than chemistry can destroy them. On Earth, the presence of both oxygen and methane in our atmosphere is a result of biological activity. Photosynthetic organisms produce oxygen, while bacteria produce methane. Without life continuously replenishing both gases, they would react together and disappear from our atmosphere within a few million years. When Webb finds similar chemical disequilibrium on distant planets, it raises quiet questions about what processes might be maintaining those gases. One of the most intriguing detections has been of dimethyl sulfide in the atmosphere of a planet orbiting a star about 120 light-years away. On Earth, dimethyl sulfide is primarily produced by ocean plankton, biological organisms that play a crucial role in our planet's sulfur cycle. Finding it on a distant planet does not confirm life. Many chemical processes could potentially produce this molecule, but it moves that planet higher on the list of worlds deserving careful follow-up observations. Other atmospheric surprises include the presence of water vapor in unexpected amounts, clouds made of minerals that would be solid on Earth, and temperature distributions that suggest vigorous atmospheric circulation patterns. Some planets have permanent day sides facing their stars and permanent night sides in darkness, with fierce winds transporting heat from the scorching day side to the frozen night side. These circulation patterns create complex weather systems that Webb can study by observing how atmospheric features change over time. The telescope has also revealed that many exoplanet atmospheres are hazy, filled with high-altitude clouds of tiny particles that obscure the lower atmosphere from our view. Understanding the composition and properties of these hazes is crucial for characterizing the planets below them. Some hazes are made of simple compounds, like water ice or methane droplets, similar to clouds on Earth. Others contain complex organic molecules called tholins, reddish compounds formed when ultraviolet light breaks apart simpler molecules and the fragments recombine into larger structures. Titan, Saturn's largest moon, has a thick atmosphere full of tholins, giving it an orange hue. Webb's detection of similar hazes on distant exoplanets suggests that complex organic chemistry is common throughout the galaxy. This chemistry does not indicate life, but it shows that the building blocks for life, complex carbon-based molecules, can form naturally in many planetary environments. The variety of exoplanet atmospheres Webb has revealed demonstrates that planets can evolve along many different pathways, producing worlds with climates and chemistries quite unlike anything in our solar system. This diversity expands our understanding of what planetary conditions might support life, and reminds us that life might adapt to environments we have not yet imagined. Some exoplanets Webb has studied exist in their stars' habitable zones, the region where temperatures could allow liquid water on the surface. But habitability depends on much more than just distance from the star. Atmospheric composition, atmospheric pressure, surface geology, magnetic fields, and stellar activity all play roles in determining whether a planet could support life. Webb's atmospheric analyses provide crucial data for evaluating these factors. The telescope's observations have also revealed unexpected connections between planet formation and stellar metallicity. Stars rich in elements heavier than hydrogen and helium tend to host different types of planets than stars with lower metallicity. This suggests that the raw materials available in a stellar nebula significantly influence what kinds of worlds can form there. As Webb continues its exoplanet survey, astronomers are building a comprehensive picture of planetary diversity across the galaxy. The data will inform future missions designed to search for biosignatures, the chemical indicators of life in exoplanet atmospheres. By understanding what kinds of planets exist and what their atmospheres naturally contain, we can better identify the planets where something unusual, something potentially biological, might be occurring. But atmospheric mysteries are not the only surprises Webb has revealed about planetary systems. The telescope's observations of planet formation regions have uncovered processes and structures that challenge our models of how worlds emerge from clouds of gas and dust. Young planetary systems are displaying structures and features that do not fit our models of planet formation. When James Webb observes star-forming regions where planets are currently being born, it can see details invisible to previous telescopes. The infrared light Webb specializes in can penetrate the thick clouds of dust surrounding young stars, revealing the protoplanetary disks where planets are beginning to condense. These disks should be relatively smooth structures, gradually transitioning from dense inner regions to thinner outer regions. Instead, Webb sees gaps, rings, spirals, and asymmetric features that suggest complex dynamics are at play. Many of these features are likely carved by newly forming planets whose gravity clears lanes in the surrounding disk as they orbit. By studying the patterns, astronomers can infer the presence of planets too small or too deeply embedded in the disk to see directly. But some structures do not fit this explanation. Spiral arms that extend too far into the disk's outer regions, asymmetries that suggest the disk is not smoothly distributed around the star, and gaps that appear too early in the disk's evolution for planets to have formed yet. These features hint at processes we do not fully understand. Gravitational instabilities in the disk itself can create structures without planets, or maybe magnetic fields threading through the disk are channeling gas into specific patterns. Another possibility is that nearby stars are gravitationally perturbing the disk, creating asymmetries as they pass. Webb has also revealed that planet formation begins earlier than expected. Some very young stars, barely a few 100,000 years old, already show signs of planetary assembly in their surrounding disks. This suggests that planets can begin forming almost as soon as the disk itself coalesces, racing against the clock before the star's radiation and wind disperse the disk material. The observations have also shown unexpected chemical gradients within protoplanetary disks. The inner regions, closer to the star, are hot enough to vaporize most molecules, leaving mainly rocky materials and refractory metals. The outer regions, colder and more distant, harbor ices, water, carbon dioxide, methane, and ammonia frozen into solid grains. The boundary between these regions, called the snow line, is where ice can exist, and it plays a crucial role in planet formation. Rocky planets like Earth form in the inner regions, while gas giants like Jupiter form beyond the snow line, where ice enhances the available solid material. But Webb's observations show that the snow line is not a simple fixed boundary. It moves inward and outward as the disk evolves, affected by changes in the star's luminosity and the disk's opacity. Planets forming in disks with dynamic snow lines might experience very different formation conditions than our models assume, potentially explaining some of the unusual exoplanets we observe. The telescope has also captured images of jets and outflows from young stars, powerful streams of matter ejected along the star's rotation axis. These jets can be hundreds of billions of miles long, punching through the surrounding cloud and dispersing material into interstellar space. Understanding these jets is important because they remove mass and angular momentum from the forming stellar system, affecting how the star and its disk evolve. Some protoplanetary disks Webb has observed are tilted relative to their star's rotation axis, a configuration that should not naturally occur. This suggests that gravitational interactions, possibly with a companion star or a massive planet, have torqued the disk into a misaligned position. Planets forming in such tilted disks might end up with unusual orbits, tilted relative to the star's equator or even retrograde, orbiting opposite to the star's rotation. As Webb continues to observe young planetary systems, it is becoming clear that planet formation is more diverse and complex than our solar system's history would suggest. Each planetary system follows its own unique path, shaped by the specific conditions of its birth environment, the nearby stellar neighbours, and countless small contingencies that accumulate over millions of years. These observations inform our understanding of how our own solar system formed 4.5 billion years ago. They also help identify Which planetary systems might be most likely to host planets suitable for life, systems where stable conditions allowed worlds to form in the habitable zone and remain there for billions of years? But beyond planetary systems, Webb's observations have also revealed surprises in stellar evolution itself. The telescope has captured phenomena that challenge our models of how stars live, die, and return their matter to the cosmos. Stars are dying in ways that do not match our theoretical predictions, and the discrepancies are forcing astronomers to reconsider stellar evolution models. When James Webb observes distant supernovae, the explosive deaths of massive stars, it can capture spectral details that reveal the composition of the ejected material, the energy of the explosion, and the processes occurring in the expanding debris cloud. Some of these supernovae are not behaving as expected. A typical Type II supernova occurs when a massive star exhausts its nuclear fuel and its core collapses, triggering a rebound explosion that blows the star's outer layers into space. The explosion should follow predictable patterns based on the star's mass and composition, with specific elements appearing in the spectrum at specific times as different layers of the star are ejected. But Webb has observed supernovae that show unexpected spectral features, elements appearing at the wrong times or in the wrong abundances, suggesting the explosion mechanisms are more complex than our models capture. One possibility is that some massive stars are rotating rapidly before they explode, and this rotation affects how the collapse and explosion proceed. Another possibility is that binary star interactions, where two stars orbit each other closely, can strip away outer layers before the supernova, changing the star's structure and altering the explosion. Webb has also observed supernova remnants, the expanding clouds of debris from stars that exploded thousands of years ago. These remnants show intricate structures, shells, filaments, and knots of material moving at different speeds and densities. By studying these structures, astronomers can reconstruct what happened during the explosion and how the debris has interacted with surrounding interstellar gas. Some remnants show asymmetries that suggest the explosion was not spherically symmetric, possibly because the collapsing core was rotating or because instabilities during the explosion channeled energy in specific directions. The telescope has also captured images of stars in the process of dying more slowly, red giants and asymptotic giant branch stars that are shedding their outer layers in stellar winds. These stars are returning material to the interstellar medium, enriching space with the heavy elements synthesized in their cores. Webb can see the complex patterns in these stellar winds, spirals and arcs created by binary companions or magnetic fields. One of the most beautiful and scientifically valuable observations Webb has made is of planetary nebulae, the glowing shells of gas surrounding white dwarf stars, the remnants left after red giants shed their outer layers. Webb's observations are also revealing unexpected details about the life cycles of stars in clusters. When thousands of stars form together in a single massive cloud collapse, they create environments quite different from the relative isolation of stars like our Sun. In dense stellar clusters, stars pass close to one another. Gravitational interactions can disrupt planetary systems, and the combined radiation from thousands of young, brilliant stars creates intense ultraviolet environments that affect how surrounding gas evolves. The telescope has observed young star clusters where these effects are clearly visible. Protoplanetary disks around stars in the cluster centers are being evaporated by the intense radiation from their neighbors, potentially preventing planet formation or truncating disks before large planets can grow. Yet some stars in these harsh environments do manage to form planets, suggesting that planet formation is a remarkably robust process that can succeed even under challenging conditions. Webb has also studied the remains of ancient star clusters, groups of stars that formed together billions of years ago and have since drifted apart. By analysing the chemical compositions and ages of these dispersed cluster members, astronomers can reconstruct the history of star formation in our galaxy, understanding when and where major episodes of stellar birth occurred. This archaeological approach to stellar astronomy reveals patterns in how our Milky Way assembled itself over cosmic time. These nebulae display remarkable variety in shape and structure, from simple spherical shells to complex hourglass shapes, bipolar lobes, and intricate filamentary structures. Each shape tells a story about the star's evolution, its rotation, its magnetic field, and whether it had a companion star. Webb's infrared sensitivity allows it to see through dust and reveal structures invisible to optical telescopes. Some planetary nebulae have multiple nested shells, evidence of episodic mass loss where the star shed material in pulses separated by thousands of years. Others show jets or fast-moving knots of gas, suggesting complex dynamics during the ejection process. By studying planetary nebulae in detail, astronomers learn about the final stages of stellar evolution for stars like our Sun, which will itself become a red giant in about 5 billion years, eventually ejecting its outer layers to form a planetary nebula. Webb's observations of stellar death connect to the larger cosmic cycle of matter. The elements heavier than hydrogen and helium that make up planets and life are forged in stellar cores and dispersed into space through supernovae and stellar winds. This enriched material becomes part of future generations of stars, planets, and potentially life. We are made of stardust, literally, and Webb's observations of dying stars show us the processes that created the atoms in our bodies. But stellar evolution mysteries represent just one category of phenomena where Webb's observations are revealing unexpected complexity. The telescope's study of galaxy centers and supermassive black holes has uncovered behaviors that challenge our understanding of these cosmic giants. Supermassive black holes at galaxy centers are consuming matter in ways that do not match our theoretical models. When James Webb observes active galactic nuclei, the bright regions surrounding supermassive black holes that are actively feeding, it can analyze the spectral signatures of the surrounding material, determining its composition, temperature, velocity, and distribution. The observations reveal that matter does not simply fall into black holes in the smooth, orderly manner our models typically assume. Instead, the accretion process is turbulent, chaotic, and highly variable. Some black holes show evidence of episodic feeding, alternating between periods of intense activity and relative quiescence. This suggests that matter arrives in clumps, perhaps stars or gas clouds being torn apart by tidal forces, creating bursts of activity as each new meal is consumed. Other black holes display outflows that seem more powerful than the infalling matter's energy budget should allow. These jets and winds are somehow extracting energy more efficiently than our models predict, possibly by tapping the rotational energy of the black hole itself through processes we are still working to understand. Webb has also observed the immediate environments around supermassive black holes, the innermost regions where matter orbits at significant fractions of light speed and where gravity is so intense that space-time curvature becomes extreme. In these regions, the light from hot gas is redshifted and blueshifted by extreme Doppler effects, stretched and compressed by the motion of the emitting material. Some of the spectral features Webb observes are broader than expected, suggesting even more extreme velocities than models predict. This could indicate that the inner accretion flow is more turbulent than we realize, with gas moving not just in orderly orbits but in chaotic, colliding streams. The telescope has also detected dust surprisingly close to some supermassive black holes, in regions where the intense radiation should vaporize any solid particles. The survival of this dust suggests it is being continuously replenished, possibly by material torn from stars that ventured too close to the black hole. Alternatively, the dust might be shielded somehow, perhaps in dense clumps or behind accretion disk structures that block some of the radiation. One of the most intriguing findings is evidence for precessing jets, beams of matter ejected from near the black hole that are changing direction over time. This precession could result from the black hole's spin axis wobbling due to gravitational interactions with surrounding matter, or with a companion black hole if the system contains a binary pair. Precessing jets would sweep across space like cosmic searchlights, potentially affecting different regions of the host galaxy at different times. Webb's observations of supermassive black holes also inform our understanding of their growth history. By analysing the spectra of active galactic nuclei at different distances and thus different cosmic eras, astronomers can trace how black hole feeding has changed over cosmic time. The data show that black hole activity peaked when the universe was a few billion years old and has generally declined since, as galaxies consumed or expelled much of their available gas. This history connects to the cosmic evolution of star formation, which also peaked several billion years ago. Both processes depend on the availability of cold gas, and as the universe has expanded and heated its gas content, both star formation and black hole growth have slowed. Understanding how supermassive black holes feed also has implications for galaxy evolution. The energy released by actively feeding black holes can heat or expel gas from the entire galaxy, quenching star formation and affecting the galaxy's long-term development. This feedback process helps explain why the most massive galaxies are generally elliptical systems with little ongoing star formation. Their central black holes grew large enough to heat all the gas and shut down the star formation that would have made them spiral galaxies. As Webb continues observing supermassive black holes across cosmic time, astronomers are refining their models of how these objects grow, how they affect their surroundings, and how they have shaped the evolution of galaxies throughout cosmic history. But black hole feeding represents only part of the story. Webb's observations have also revealed surprising phenomena in the space between galaxies, phenomena that suggest the intergalactic medium is more dynamic and structured than we realized. The intergalactic medium contains more matter and energy than expected, and it is displaying behaviors that challenge our understanding of large-scale cosmic structure. When James Webb studies the vast spaces between galaxies, it is not observing empty void, but a diffuse sea of gas, plasma, and perhaps other components we have not yet identified. This intergalactic medium is difficult to observe because it is so tenuous, millions of times less dense than even the space between stars in a galaxy. But Webb's sensitivity allows detection of faint emissions from this material, revealing its distribution and properties. The observations show filamentary structures connecting galaxy clusters, exactly as the cosmic Webb model predicts. But the filaments are warmer and contain more matter than cosmological simulations suggest they should. This discrepancy might indicate that our simulations are not fully capturing the physics of how gas behaves in these environments, possibly underestimating heating mechanisms or missing feedback processes that pump energy into the intergalactic medium. Another surprise is the detection of strong turbulence in some intergalactic regions. Gas is not sitting quietly in the filaments, but is moving in complex, chaotic patterns suggestive of shock waves and instabilities. These could be driven by galaxies moving through the intergalactic medium, stirring it like boats moving through water, or by energy injected from supermassive black holes that extends beyond their host galaxies. Webb has also found evidence for magnetic fields threading through intergalactic space, much weaker than even Earth's magnetic field, but extending over such vast distances that their total energy is substantial. These fields could play a role in channeling gas flows along filaments, and might affect how cosmic rays, high-energy particles accelerated by various cosmic processes, propagate through the universe. The origin of these intergalactic magnetic fields is uncertain. They might be primordial, seeded during the very early universe and then amplified by cosmic structure formation. They might be generated by astrophysical processes, perhaps stretched and carried into intergalactic space by outflows from galaxies and black holes. One of the most significant discoveries is that the intergalactic medium contains a substantial fraction of the universe's missing baryons, the ordinary matter that observations and theoretical calculations indicate should exist, but that has been difficult to locate. For years, astronomers have known that the amount of ordinary matter they could directly observe in stars, gas, and dust was less than the amount that should exist based on measurements of the early universe's composition. Webb's detection of warm diffuse gas in intergalactic filaments helps account for much of this missing matter. It has been hiding in plain sight, so diffuse and cool that it did not emit enough light to be easily detected until Webb's sensitive instruments surveyed the intergalactic medium systematically. The discovery that the intergalactic medium is more substantial and dynamic than expected affects our understanding of galaxy evolution. Galaxies are not isolated systems, but are constantly exchanging matter with their surroundings, pulling in fresh gas from intergalactic filaments to fuel star formation and ejecting processed gas back into the intergalactic medium through stellar winds and supernova explosions. This cycle of inflow and outflow, mediated by the intergalactic medium, regulates how galaxies grow and evolve over billions of years. Webb's observations of the intergalactic medium also provide data for testing cosmological models. The distribution and properties of intergalactic gas depend on factors like dark matter distribution, the universe's expansion history, and the effects of dark energy. By comparing observations with simulation predictions, researchers can constrain these cosmic parameters and test whether our standard cosmological model accurately describes the universe's large-scale structure. As Webb continues its survey of intergalactic space, we are gaining a more complete picture of the universe's matter budget, understanding where all the ordinary matter resides and how it flows through cosmic structures over time. But the intergalactic medium is only one component of the cosmic inventory. Webb's observations have also provided new insights into dark matter and dark energy, the mysterious components that together make up 95% of the universe's total mass energy content. The telescope's discoveries about galaxies, cosmic structure, and expansion rates are providing clues about these fundamental cosmic mysteries. Dark matter and dark energy remain enigmatic, but Webb's observations are helping narrow the range of possible explanations for these cosmic mysteries. Dark matter, the invisible substance that makes up about 27% of the universe's mass energy content, only interacts through gravity, making it extraordinarily difficult to study directly. But its gravitational effects are everywhere, holding galaxies together, shaping cosmic structure, and bending light through gravitational lensing. Webb has captured remarkable images of gravitational lensing, where massive galaxy clusters act as cosmic magnifying glasses, bending and amplifying the light from more distant galaxies behind them. By analyzing the patterns of these lensed images, astronomers can map the distribution of dark matter in the clusters, revealing its structure and clumping behavior. The observations show that dark matter is not smoothly distributed, but forms complex structures, halos around galaxies, filaments connecting clusters, and dense concentrations in galaxy cluster cores. Some of these dark matter distributions match predictions from simulations based on the assumption that dark matter is cold, meaning its particles move slowly compared to light speed. But other observations show discrepancies, particularly on small scales, that might indicate our cold dark matter model needs refinement. One ongoing puzzle is the core cusp problem. Simulations predict that dark matter halos should have dense central cusps, with density increasing sharply toward the center. But observations of some galaxies suggest their dark matter halos have flatter cores, with more uniform density in the central regions. Webb's gravitational lensing observations have also revealed something unexpected about the distribution of dark matter on the smallest scales that can be measured. Some lensing patterns show tiny distortions that suggest the presence of compact dark matter structures much smaller than galaxies. These could be primordial black holes, dense clumps of dark matter, or even more exotic objects that have not yet been identified. The nature of these small-scale structures could provide crucial clues about what dark matter actually is. One particularly intriguing possibility is that these small structures are the remnants of the very first objects to form in the universe, condensing from slight density variations in the cosmic matter distribution. If so, they would be fossils from cosmic dawn, preserving information about conditions in the universe's earliest moments. Alternatively, they might be continuously forming structures, condensing from dark matter as it flows through the cosmic web. Understanding which scenario is correct would tell us whether dark matter is relatively simple in its behavior or capable of complex structure formation across all scales. This discrepancy might indicate that dark matter interacts with itself weakly through forces other than gravity, a possibility called self-interacting dark matter. Or it might be that complex feedback processes involving star formation and supernova explosions can redistribute dark matter in galaxy centers, smoothing out the cusps predicted by simple simulations. Webb's observations of distant galaxies and cosmic structure provide data that can help distinguish between these possibilities. By studying how dark matter is distributed in galaxies at different cosmic eras and in different environments, astronomers can test whether dark matter behaves exactly as the simplest models predict, or whether its properties are more complex. The telescope's discoveries about impossibly massive early galaxies and premature black holes also have implications for dark matter. If these structures formed more quickly than expected, it might indicate that dark matter in the early universe was clumpier or behaved differently than our models assume, providing gravitational seeds that allowed rapid structure formation. Dark energy, the even more mysterious component that makes up about 68% of the universe's mass energy content, is responsible for the accelerating expansion of space that Webb's observations have helped quantify. Understanding dark energy is one of the deepest challenges in modern physics, as we have no confirmed theoretical explanation for what it is or why it has the properties it appears to have. Webb's precise measurements of cosmic expansion at different distances and different cosmic epochs provide crucial data for constraining dark energy models. The simplest possibility is that dark energy is a cosmological constant, a property of space itself that creates a uniform repulsive effect throughout the universe. But Webb's discovery of expansion rate discrepancies raises the possibility that dark energy might not be constant, but could vary over time or in different regions of space. If dark energy's strength has changed over cosmic history, it would affect how galaxies and cosmic structure formed and evolved. Webb's observations of distant galaxies, which show us the universe billions of years ago, can be compared with observations of nearby galaxies to search for evidence of dark energy evolution. So far, the data are consistent with a constant dark energy, but uncertainties remain, and more observations will help tighten constraints. Another possibility is that dark energy is not a new form of energy at all, but a sign that our theory of gravity, general relativity, breaks down on cosmic scales. Modified gravity theories propose that gravitational interactions behave differently over very large distances, producing acceleration that looks like dark energy but actually results from different gravitational physics. Webb's observations of cosmic structure, gravitational lensing, and expansion can help test these alternatives. Different theories make different predictions about specific observables, and as Webb accumulates more data, some theories will be ruled out while others remain viable. The combination of dark matter and dark energy in our universe has profound implications for cosmic fate. If dark energy remains constant, the universe will continue expanding forever at an accelerating rate, eventually becoming so dilute and cold that no new structures can form. If dark energy evolves, the universe's fate could be quite different, potentially ending in a big rip where space expands so rapidly that it tears apart galaxies, stars, and eventually atoms. Alternatively, dark energy could weaken or reverse, potentially leading to a future contraction. Webb's observations cannot predict the universe's ultimate fate with certainty, but they provide crucial data that makes our predictions more informed and helps us understand the cosmic trajectory we are following. The mysteries of dark matter and dark energy remind us how much remains unknown about the universe's fundamental nature. These substances together dominate the cosmic mass-energy budget, yet we do not know what they are made of, where they came from, or why they have their observed properties. Webb's discoveries are gradually constraining possibilities and pointing toward answers, but the full resolution of these mysteries will likely require breakthroughs in both observation and theory. Meanwhile, the telescope continues exploring, revealing more about the cosmos we inhabit and the forces that shape it. But beyond dark matter and dark energy, Webb has made discoveries that touch on perhaps the most profound question of all: whether we are alone in the universe. The telescope's observations of potentially habitable worlds and the conditions for life are informing our understanding of where and how life might emerge. James Webb's discoveries are reshaping our understanding of where life might exist in the universe, though no definitive biosignatures have yet been detected. When the telescope analyzes exoplanet atmospheres, it is searching for combinations of gases that might indicate biological activity. On Earth, the simultaneous presence of oxygen and methane is a biosignature maintained only because living organisms continuously produce both gases. Without life, these reactive molecules would quickly combine and disappear from the atmosphere. Webb has the sensitivity to detect similar biosignatures on nearby exoplanets if they exist. The search focuses on planets orbiting small cool stars called red dwarfs, because these stars are dim enough that their planets need to orbit very close to receive adequate warmth. This close orbit makes the planets easier to observe, as they transit in front of their stars more frequently and their atmospheres are more readily detectable. Several red dwarf systems with potentially habitable planets have been studied in detail. The results so far show no clear biosignatures, but the observations have revealed diverse atmospheric compositions that expand our understanding of planetary climates. Some planets have thick atmospheres that might trap too much heat, creating runaway greenhouse effects. Others have thin atmospheres that might not provide enough insulation, leaving their surfaces frozen. The quest for biosignatures is complicated by the fact that we are searching based on Earth's example, the only life we know. But life elsewhere might use different chemistry, produce different gases, or exist in environments we have not imagined. Some researchers propose searching for industrial signatures, atmospheric pollutants that could indicate technological civilization. Others suggest looking for anomalous surface features that might indicate agriculture or large-scale engineering. Webb's observations also inform our understanding of habitability more broadly. The telescope has revealed that many exoplanets are bombarded by intense radiation from their host stars, particularly planets around red dwarfs, which often produce powerful flares that could strip away atmospheres and sterilize surfaces. Whether life could emerge and persist on such worlds depends on factors like atmospheric mass, magnetic field strength, and the potential for organisms to shelter underground or underwater. The discovery of diverse planetary types, from hot Jupiters to mini Neptunes to super-Earths, shows that planet formation produces a wide range of outcomes. Somewhere in this vast catalogue of worlds, conditions might align to allow life to emerge, evolve, and perhaps develop technology. Webb's survey is still in its early phases. Each new exoplanet observation adds to our understanding of planetary diversity and habitability. Future observations will target the most promising candidates, spending extended time analysing their atmospheres in detail, searching for the subtle spectral signatures that might indicate something extraordinary is happening. Beyond individual planets, Webb's discoveries about galaxy formation, stellar evolution, and cosmic structure inform our understanding of where in the universe conditions might be favorable for life. Regions with high supernova rates might be too dangerous, with frequent sterilizing radiation. Regions with low metallicity might lack the heavy elements needed for planet formation. The galactic habitable zone, the region of a galaxy where conditions are most favorable for life, might be more constrained than we thought. Our solar system's location in the Milky Way, about halfway out from the galactic center in a relatively quiet spiral arm, might be more special than we realized. Webb's discoveries about cosmic violence, wandering black holes, rogue planets, and rapid galaxy mergers paint a picture of a universe that is often hostile to stable, long-lived planetary systems. The fact that Earth has remained habitable for billions of years might require more fortunate circumstances than we appreciated. Yet the universe's vast scale suggests that even rare conditions might occur countless times. With hundreds of billions of galaxies, each containing hundreds of billions of stars, many with planets, the total number of worlds is almost incomprehensible. Even if only a tiny fraction are habitable, that might still amount to countless worlds where life could arise. Webb cannot answer whether we are alone, but its discoveries frame the question in new ways, helping us understand what we should be looking for and where we should look. The search for life beyond Earth continues, guided by the telescope's revelations about the cosmos we inhabit. But even as Webb expands our understanding of potentially habitable worlds, its observations have also revealed phenomena that challenge the very foundations of physics. The telescope's discoveries about space-time behavior in extreme environments are pushing theoretical physics in unexpected directions. Space-time is behaving in unexpected ways near extreme cosmic objects, and the observations are challenging fundamental physics. When James Webb observes regions near black holes, neutron stars, and other extreme environments, it can detect subtle effects that arise from the severe warping of space-time in these locations. General relativity, Einstein's theory of gravity, predicts how space-time should curve around massive objects and how that curvature affects light, matter, and the flow of time. But some of Webb's observations show effects that do not quite match standard predictions. Subtle discrepancies that might indicate our understanding of gravity needs refinement, particularly in extreme regimes. Near supermassive black holes, light undergoes gravitational redshift, losing energy as it climbs out of the deep gravitational well. Webb can measure this effect by comparing spectral features from different regions around black holes. Some measurements show redshifts slightly larger than predicted, possibly indicating that the space-time curvature is more severe than models assume, or that additional physics beyond general relativity becomes important in these extreme environments. Another intriguing observation involves frame dragging, an effect where rotating massive objects literally twist space-time around them, pulling nearby matter into rotational motion. Near spinning black holes, frame dragging becomes intense, affecting the orbits of surrounding matter and creating observable signatures in the emitted light. Webb's observations of matter orbiting close to black holes sometimes show features consistent with stronger frame dragging than expected, perhaps indicating that these black holes are spinning faster than models predict, approaching the theoretical maximum rotation rate allowed by general relativity. The telescope has also observed gravitational lensing with unprecedented precision, measuring how light from distant galaxies is bent by intervening massive structures. In most cases, the observed lensing matches general relativity's predictions beautifully, confirming the theory's accuracy. But a few unusual cases show lensing patterns that are difficult to explain, possibly indicating complex dark matter distributions or, more provocatively, hints of deviations from general relativity on specific scales. One of the most profound observations involves time dilation effects. Clocks run slower in strong gravitational fields, a prediction of general relativity that has been confirmed countless times. Webb can observe this effect by comparing the rates of astrophysical processes in different gravitational environments. Some high-energy phenomena near black holes appear to evolve at rates that test our understanding of extreme space-time curvature. The telescope's observations of colliding black holes, studied indirectly through their effects on surrounding matter, provide tests of general relativity in the most extreme regime possible, where gravity is so strong that space-time itself becomes turbulent and dynamic. These observations complement gravitational wave detections, which directly measure the ripples in space-time from such collisions. Together, electromagnetic and gravitational wave observations are building a comprehensive picture of how gravity behaves when pushed to its limits. Some theoretical physicists have proposed that at extremely small scales, or in extremely strong fields, quantum effects might become important for gravity, leading to a quantum theory of gravity that modifies general relativity's predictions. Webb's observations of extreme environments provide data that could potentially reveal such effects if they exist, though detecting unambiguous signatures of quantum gravity remains one of the greatest challenges in physics. The study of extreme space-time also has implications for the nature of black hole event horizons, the boundaries beyond which nothing can escape. Some theories propose modifications to black hole physics that would alter the properties of event horizons or even replace them with different structures. Webb's observations of matter near black holes can help test these ideas by showing whether matter behaves as general relativity predicts or displays anomalies that might indicate new physics. As Webb continues observing extreme cosmic environments, it is essentially conducting experiments in regimes of gravity that cannot be reproduced in any laboratory. These natural cosmic laboratories allow us to test fundamental physics under conditions billions of times more extreme than anything we can create on Earth. The observations might eventually reveal whether general relativity is the complete story of gravity or whether deeper theories await discovery. But space-time phenomena are not the only area where Webb's observations are probing fundamental physics. The telescope's discoveries have also raised questions about the stability of the vacuum itself and whether the universe we inhabit is in its most stable state. Webb's observations of high-energy phenomena are providing data relevant to questions about vacuum stability and the fundamental nature of space-time. In quantum field theory, empty space is not truly empty, but filled with quantum fields in their lowest energy states. This quantum vacuum can have different possible configurations, and physics suggests that our universe might be in a metastable state, stable enough to persist for vast timescales, but not the absolute lowest energy configuration possible. If the universe is in a metastable vacuum state, quantum processes could potentially trigger a transition to a lower energy state, a phase transition that would propagate through space at light speed, fundamentally altering the properties of matter and the laws of physics as we know them. The likelihood of such a transition depends on the precise properties of fundamental particles and forces, particularly the mass of the Higgs boson and the behavior of fields at extremely high energies. Webb's observations of the early universe, when matter was denser and temperatures were higher, provide data about physical conditions approaching those where vacuum stability becomes relevant. If the universe passed through phase transitions in its early history, those transitions might have left signatures that Webb can detect, subtle patterns in the distribution of matter or anomalies in the cosmic microwave background. The telescope's study of cosmic rays, high-energy particles that zip through space, also informs our understanding of vacuum stability. If cosmic rays with sufficient energy collided with quantum fields in just the right way, they could theoretically trigger a vacuum collapse. The fact that such collapses have not occurred despite billions of years of cosmic ray bombardment suggests that either our vacuum is more stable than some theories predict, or the energy threshold for triggering a collapse is higher than those theories estimate. Webb's observations of extremely energetic cosmic phenomena, such as gamma-ray bursts and active galactic nuclei, help constrain the energy scales involved in fundamental physics. These cosmic accelerators produce particles with energies far exceeding anything possible in human-made colliders, providing natural experiments that test physics at extreme scales. The discoveries about rapid galaxy formation, premature black holes, and unusual cosmic expansion also touch on questions about the early universe's physics. The first fraction of a second after the Big Bang was governed by physics we do not fully understand, involving energies and densities where quantum effects and gravitational effects were equally important. If processes during that era were different from what our theories predict, they could have left signatures that affect cosmic structure formation and the universe's subsequent evolution. One particularly intriguing possibility is that the universe experienced phase transitions in its earliest moments that created different domains with slightly different physical properties. If our observable universe is just one domain within a much larger cosmos, and if other domains have different vacuum states or even different physical constants, it would explain some of Webb's puzzling observations about cosmic structure and expansion. This scenario connects to the idea of eternal inflation, a cosmological model where the Big Bang was not a single event, but an ongoing process creating bubble universes with varying properties. Our universe would be one such bubble, and its properties, including its vacuum state, expansion rate, and structure formation history, would reflect the specific conditions under which our bubble formed. Webb cannot directly observe other bubble universes if they exist, but the telescope's discoveries about our universe's properties can help determine whether the multiverse scenario is necessary to explain what we see, or whether simpler explanations suffice. The study of vacuum stability and fundamental physics represents the deepest level of inquiry Webb's observations enable. By revealing how matter and energy behave under extreme conditions and at vast scales, the telescope provides clues about the bedrock principles underlying reality. The discoveries might not immediately answer fundamental questions, but they constrain possibilities, eliminate some theories, support others, and point toward the investigations needed to deepen our understanding. As we continue exploring the cosmos through Webb's infrared eyes, we are simultaneously exploring the limits of physics itself, testing whether the laws we have discovered on Earth truly govern the entire universe, or whether reality holds surprises at scales and energies beyond our current theories. The implications of Webb's discoveries extend beyond astronomy and physics, touching on philosophy and our place in the cosmos. James Webb's revelations challenge not just scientific models but our philosophical understanding of existence and our place in the cosmic order. The discoveries of impossibly massive early galaxies, premature black holes, and coordinated galactic rotation suggest that the universe might be more organized and structured than the standard cosmological model assumes. If these patterns reflect underlying principles we have not discovered, it raises questions about whether the cosmos follows deeper laws than we currently recognize. The possibility that our universe might be the interior of a black hole within a larger cosmos, suggested by several lines of evidence Webb has provided, transforms our understanding of cosmic significance. We would not be inhabitants of the universe, but rather residents of one bubble within an incomprehensibly larger structure. Everything we can observe, from the cosmic microwave background to the most distant galaxies, would be phenomena occurring within our local pocket of space-time, forever disconnected from whatever lies beyond our cosmic horizon. This scenario would make the question of what exists outside our universe permanently unanswerable through observation. We could speculate, construct theories, search for indirect evidence, but we could never directly observe or interact with anything beyond our bubble. The philosophical implications are profound. If we are cosmically isolated, it changes how we think about our place in existence and the limits of what knowledge is possible. Webb's discoveries about cosmic violence, wandering black holes, frequent galaxy mergers, and unstable space-time also affect how we view our cosmic neighborhood. The universe is not a safe, stable garden, but a dynamic arena where catastrophic events are common and where stability is a fortunate accident rather than a guaranteed condition. Earth's billions of years of relative stability, the peaceful evolution that allowed life to emerge and diversify, might be more contingent and fragile than we appreciated. This realization adds urgency to questions about humanity's long-term survival and our potential expansion beyond Earth. The discoveries also highlight the vastness of what remains unknown. Despite centuries of scientific progress, Webb's first years of operation have revealed phenomena that require fundamentally rethinking our cosmological models. If our understanding of the universe's basic properties, its expansion rate, its structure formation timeline, its fundamental forces, is this incomplete? What else have we missed? The universe's capacity for surprise, its ability to present us with objects and behaviors that violate our expectations, suggests that reality is far richer and more complex than even our most sophisticated theories capture. This should inspire humility about the limits of our knowledge and excitement about the discoveries that await. Yet the continuing refinement of our understanding also demonstrates the power of the scientific method. Each puzzle Webb reveals becomes a focus for investigation, driving new observations, refined theories, and deeper understanding. Science advances not despite these mysteries, but because of them. The discomfort of not knowing, the challenge of unexplained observations, these drive the process of discovery that gradually expands human knowledge. Webb's discoveries about potential biosignatures and habitable worlds add another philosophical dimension. The question of whether we are alone in the universe is perhaps the most profound unknown we face. If life is common, the cosmos is a vibrant place, filled with diverse organisms and perhaps intelligences that have developed their own understanding of reality. If life is rare, Earth's biosphere becomes cosmically precious, a fragile island of complexity in an overwhelmingly barren universe. Either answer transforms how we view ourselves and our cosmic significance. Webb cannot yet answer this question definitively, but every observation that reveals another potentially habitable world, every analysis that shows complex chemistry occurring on distant planets, adds context to the possibilities. The discovery that the universe achieved complexity earlier than expected, that galaxies and stars could form rapidly, suggests that the cosmic timeline for life might be longer than we thought, with more opportunities for life to emerge, evolve, and perhaps develop intelligence and technology. As we absorb the implications of Webb's discoveries, we are reminded that astronomy is not just about cataloguing distant objects, but about understanding our place in the cosmos. Every galaxy Webb images, every spectrum it captures, every mystery it reveals adds to the story of where we came from, how we came to exist, and what our cosmic context means for our future. The universe James Webb reveals is stranger, more violent, more organized, and more mysterious than we imagined. But it is also the only reality we have, and understanding it, embracing its complexity and its surprises, is essential for navigating our cosmic future. The telescope continues its observations night after night, pointing its mirror toward different regions of space, gathering photons that have traveled for billions of years to reach us. Each observation adds detail to our cosmic map, answering some questions while raising new ones, gradually building a more complete and accurate picture of the universe we inhabit. The journey of discovery that Webb has begun will continue for years, perhaps decades. The telescope was designed to operate for at least 10 years, though it might function much longer if its systems remain healthy. Every year of operation will bring new observations, new discoveries, new puzzles to contemplate. Future observations might finally detect definitive biosignatures on a distant world, or reveal the nature of dark matter and dark energy, or discover objects even more puzzling than those already found. The cosmos is vast, and we have only begun to explore it in detail. Meanwhile, the discoveries Webb has already made are being integrated into our understanding of the universe, reshaping textbooks, informing new missions, and inspiring future generations of scientists who will continue the work of cosmic exploration. As you drift towards sleep, consider the vast cosmos Webb has revealed. Ancient galaxies rushing through space, their stars numbering in the billions. Black holes wandering through the darkness, warping space-time with their immense gravity. Rogue planets broadcasting signals into the void. Cosmic filaments stretching across incomprehensible distances, connecting galaxies in an intricate web. The universe is more complex and more wondrous than we imagined, full of phenomena that challenge our understanding and invite further exploration. We are fortunate to live in an era when technology allows us to observe these cosmic mysteries, when instruments like James Webb can peer across billions of light years and billions of years of time, showing us the universe's history written in starlight. The night sky is not a distant backdrop, but a window into the cosmos, and every point of light you see, every star and galaxy, has its own story, its own history of formation, evolution, and transformation. As you rest, those distant worlds continue their cosmic dance. Stars continue to form and die. Galaxies continue their slow gravitational ballet, and the universe continues its expansion, carrying everything slowly apart while new structures continue to form. You are part of this cosmic story, made of atoms forged in ancient stars, living on a world that formed from cosmic dust, looking out at the universe with eyes that evolved to see light that has travelled unimaginable distances to reach you. Sleep well, knowing that the cosmos is vast, ancient, and full of wonders waiting to be discovered. The mysteries Webb has revealed are invitations to deeper understanding, and the journey of cosmic exploration continues, always revealing new horizons, always inviting us to look farther, think deeper, and embrace the beautiful complexity of the universe we call home.